here. Let's kick it off. Welcome. Thank you for joining us today for the next simulation presentation. I'm sure you guys have seen some really cool stuff related to simulation, and hopefully I can show you some more. I want to welcome all those joining us on the live stream. It's really cool to be able to be broadcast out on the web there, and a special shout out to, I have to do this, sorry, shout out to my family, my wife and kiddos, and my mom, so love you guys. I've been using these products, these simulation products, since the 1999 release, so quite a bit of experience seeing these products grow through the years. My name's Kurt Kurtin. I'm a product manager for computer-aided technology. Happy to be with you here today, and we're going to talk about simulation once again. So I know there's a lot of good experience in the room here. I took a poll a little earlier. A lot of the folks in the attendance are regular sim users, so that's great to see that. So my presentation is going to be more of a kind of a show you some stuff that you may have missed. It won't be a training style kind of a thing. So I'll move pretty fast, but if you have any questions about anything that you saw along the way, don't hesitate to come and talk to me afterwards. I'd be happy to share my knowledge with you. We've got lots to cover, so let's get right into it. So, you know, the releases come through. We get a lot of extra material in the simulation products. We may have missed some of that stuff. You know, sometimes you're focused, you're dialed into your job, and the new releases come out, and next thing you know, you don't see half of the new stuff that comes out. And there's some really cool stuff. So my objective is to introduce you to that stuff if you haven't seen it. Encourage you to use it and hopefully build some confidence level there for you. So, and if along the way, if that tagline comes to mind, I didn't know we could do that, then just shout it out. I'd love to hear it, and it'll make me very happy. So we'll keep it light, and like I say, it'll move pretty fast. So hold on, here we go. A little bit of background on me. I got a mechanical engineering degree from Texas Tech University, dreamed of working in the aerospace industry, was able to do that, started working for Lockheed in the Houston area for a contractor at Johnson Space Center, worked on payload integration work, did a lot of analysis related to payloads. You see the payload here, it's called the large format camera. This is pre-digital camera. This is a high resolution camera. The camera and the Starfield cameras that were associated with it and the other hardware weighed about 3,400 pounds. So that structure's cantilevered off of that main payload carrier back there, and so we had to do some analysis on that. I was able to work with a senior engineer working in finite elements for the first time right out of college, and it was just a thrilling experience. Mr. Alder from the Kickstarter, one of the Kickstarter founders yesterday at the keynote, had a phrase, and it really struck home. It said, "Our history kind of informs our future." I think that was the gist of the quote. And that really struck with me because, you know, my first experiences with finite element analysis with the aerospace have stuck with me, and it's a passion of mine, and it has carried through. So payload work, payload integration, this was in the mid-'80s, and if you may recall, in January of '86, we had the tragic loss of the Challenger 7. So 6 months into it, I'm working on these payloads, and now Challenger happens. We lost some brave astronauts, and things related to payload work were cut off abruptly and on hold for about 3 years. So very unfortunate there. The good thing is that the space station work was ramping up. We were starting the process of understanding how to build up the space station and what we're going to do to bring those two together, the shuttle, the orbiter, and the space station. So there again, I'm jumping into some more simulation here now with docking the two vehicles and studying things like plume impingement and closing velocities and making sure that those two can come together safely. A little side story about that. We would work in this simulator. It was an on-orbit simulator. It simulated the aft part of the crew compartment where they controlled everything on orbit, and had the privilege of working with a lot of really cool astronauts and some other aerospace leaders. And one of those guys was John Young. Does anybody know who John Young is? Raise your hand if you're familiar with who John Young is. We have one up here. John Young was probably, I think it was in, maybe you can correct me if I'm wrong, I think he was in the second astronaut school, the second group of astronauts. He flew on 2 Gemini missions. They studied how to get vehicles docked together in Earth orbit. 2 Apollo missions. He went to the moon and studied, understood, and worked through docking there. Went back a second time and actually walked on the moon. He also flew 2 shuttle missions. So he's probably had the biggest, I think he had the longest career in aerospace as an astronaut, and has done some really amazing things. He flew the inaugural flight of the space shuttle itself. So we're in this room doing these docking simulations. I'm right out of college, 6 months out of college, and we're briefing these astronauts across a little desk that we're sitting across from them. They come in, we brief them, they go into the simulator, they do their thing, and we get data, we process the data, et cetera. Well, one day in walks Mr. John Young. So you can think about me feeling like a freshman basketball player and going to the gym and meeting Michael Jordan and teaching him how to drive the lane and make a dunk or something. It was a very overwhelming and very enjoyable experience working with them. Got a master's in mechanical also from Texas A&M University. Switched gears a little bit, went in the oil field. They say in the aerospace industry, it's got to fly, it's got to be light. In the oil field industry, all bets are off. If it doesn't work, put more steel in it, right? So total change there. Worked on some metal sealing applications for high pressure, high temperature oil well equipment. After that, landed up in the sunny Southwest in New Mexico, did some consulting work and some design and prototype build type work for companies related to the national laboratories there in New Mexico. Ended up with a reseller, and that's where I am today. I started in 2005 as a reseller focusing on simulation type products. And now I'm currently the product manager for computer-aided technology for simulation products. So anything sim, I can probably help you out. All right, so enough about me. Let's talk about you. Let's get some interaction here. I want to make sure everybody doesn't fall asleep. I know it's right after lunchtime. We're going to see some heads nodding. So a little poll for you. I want to see who's used simulation the longest, okay? I want to see if we can narrow that down. So if you've been using simulation 2020, who's using 2020 right now? Simulation products, okay? Let's go back the previous year, 2019, okay? And we're going to keep going back. If you are using or have used one of the older products, keep your hand up. So let's go 2018, okay, 2017. Okay, great, lots of veterans. Let's go back 2016. We're going to get it down to just a few here. We still have a few, all right. Did I say 2016? I think I did. 2015. Keep your hand up if you've used 2015. 14, 13, 12. All right, who we have? Okay, you guys don't count in the back, sorry. We have one left, the last man standing there. Which release have you used? 2012. Anybody used a release older than 2012? A couple here. What have you used?
I think it was probably like 2010, back when it was Cosmos Works. Or
2010. And what about you, sir? 2010? Okay, anybody have used an older release than that? Guys, come on up. I got a little something for you. You veteran users here. Thanks for indulging me in that. What's your name?
Stephen White.
Stephen?
Yeah.
Here you go.
Thanks, sir.
Adam.
And? Adam?
Yeah.
A little duffel bag there for you. Thanks a lot. Appreciate it. Give them a hand, guys. All right. So this is kind of what we're up to today. We're going to look at these this number of releases, looking back at the past there. So here's where we're heading with it. I'm going to give you some numbers that are related to those releases, new stuff that's came up that you may have missed. I'll give you some numbers. We're engineering geeks here. We got to have a few bar charts and numbers, so we'll give you some of that. Then we'll jump into the software. I'm going to show you some highlights from those 3 products, and hopefully we can get you some new information that you weren't aware of. So by the numbers, let's look at by the numbers. Well, we're going to look at those 3 products: simulation, flow, and plastics. That's what we're going to focus on for the past 5 releases. And For that combination of product and release level, we've had 117 enhancements listed in the What's New documentation. So that's a lot of stuff, right? And we're going to see every single one of them right here today, so hold on. Just kidding. So let's jump into the, oh yeah, before a shout out for anyone here in the room that's a SOLIDWORKS employee related to simulation, either tech support, technical management, we have one in the back. Anybody else from SOLIDWORKS right here? Okay. Let's give these folks a hand for the hard work they do to bring this product to us. We got some great tools that they've provided. So here's how I came up with the numbers I'm about to show you. I opened all the What's New PDF documents. If you go under the help file, there's a What's New. You can open these in all the releases that you've seen. So I grabbed the PDF. I went to each of the sections for flow, sim, or plastics. I grabbed all the bullets and I made up these categories on my own here, categories for grouping them, pulled the bullet points, put them in a big spreadsheet, and threw them all up into a pivot table, and here's how it ended up. So for the past 5 releases, you see a lot that came into play with 2017, and 2020 is really strong too, so a lot of stuff that's come along. Breaking that down into those categories that I mentioned, we've got the user interface changes or improvements, and then the ease of use as well. So, you know, SOLIDWORKS mantra is, you know, let's get this in the design process, get these tools in the design process early on. Get the designer to start looking at their work, go all the way up to the analyst and put these tools in their hands. So that's testimony to that effort there. Look, breaking down by product, you see the breakdown there. Simulation gets the lion's share of the 117. And looking at those related to the breakdown of the categories as well, you know, you see the same there, the same trend there for ease of use and user interface type stuff. All right, so here's the products that we're going to dig into. We're going to start looking at these a little bit more detail. And so I'll show you this plastic injection molding of an insert overmolded part. And we'll look at the flow simulation, a couple of different models there, and simulation, some good stuff in there as well. Jumping into plastics, without further ado, a little bit about the lineage, the history of the product, how it came into play for us, and then study management. I'm going to show you some screenshots of that, and then we'll jump into the program with some live demos. So this is the plastics product. It's our injection molding designed for manufacturing type simulation tool. The plastics tool came into the mix for us in 2012. It was a result of Dassault buying the Simpo product, the French company that had the injection molding tool. A couple of releases into it, a lot of effort went into making that product like SOLIDWORKS products, more consistency. So a lot of effort went into it there. 2020, the latest release, they've really done a great job of really sewing that up, and now our plastics product has that good look and feel and consistency that we're used to. In fact, if you open a 2019 or older project from plastics with the newest release, you'll be able to view those results if you have them, but you won't be able to make changes. You have to start a new project. It's that new of an interface, and it's that much improved. So they had to kind of cut off the older ones, and you have to kind of start from scratch if you're going to open a legacy file in 2020. Study management is greatly improved. Who uses simulation here? FEA, simulation product, the FEA tool. Okay, we've got quite a few users. We've got that consistent interface there where we've got the study tab up there, the study icon in the command manager for simulation. We quickly pick that. We get the ability to name our study, pick the study type, and off we go. So that's a familiar thing. It's been with us for a long time. Flow simulation users, any flow sim users out there? Okay, good. Got a few of those. Flow simulation, same kind of thing. We've got a command manager tab. We've got a button for either starting a new project or using the wizard to get going. And if you're new to flow simulation, I highly recommend using the wizard. It's a very good interface for getting your project going, getting it started. So consistency between those two, but it hasn't been there for plastics until 2020. So new for 2020, the command manager has very good study management that we're used to for the other products. So Very, very strong consistency there. We start a new study, we name it, we pick the mesh type, off we go. So really good stuff there. The tutorials and help category, we now have tutorials in plastics. We didn't have them before, and that was a little bit frustrating. If you wanted to get started, you had to kind of, fumble through it, or when you're waiting on taking a class, you had to get help from your reseller or whatever. Now you can get started with operations from basic filling all the way to the cooling and warpage calculations. So there's 9 tutorials there. Help files are greatly expanded. We can pick on that link for the little question mark when you're working with the program. You get right into the help file, and it's been greatly expanded. All right, so let's jump into the cool stuff. Let's see it in action. And you'll notice that these categories here are, these releases are 2019 and 2020, so that's kind of a reflection of what I was just saying about, the interface has really changed. It's made much more consistent, but so the stuff that has afforded that has come in the last 2 releases. So let me jump into SOLIDWORKS here, and here's our injection molded part. It's an insert over molded part. That's a capability that we have with our professional line of plastics, I believe. That's when it comes into play. And so, we've got a multi-body part here, if you're familiar with multi-bodies. We've got 3 bodies in here that represent the runner and sprue, the part itself, and then the insert. I'm going to go to my add-ins list, and there again, as I said, I'm going to go pretty fast. It's not really a tutorial kind of a session. It's more of a, hey, look at what we can do here. This is cool stuff. Go check it out. Plastics Command Manager tab, there's our new study button that I mentioned. I'm going to keep my default name and just roll on with it. So the big change, if you've used, and I forgot to ask, who's a plastics simulation or a plastics user, SOLIDWORKS Plastics? Do we have any in the house here? Any plastics users?
Hope to be. Does that count?
What was that?
Hope to be.
Hope to be, good. Okay, that counts too. If you had used the previous releases, this interface is greatly improved and streamlined to where you can really get things done in an orderly fashion without a lot of steps along the way. So the plastic domains, the domains node, what they call it here, I can assign nodes here. So nodes are just, what part of this problem am I setting up? So this one is the insert body, and I'll just designate that to the program. And here's my cavity, here's my runner. Pretty straightforward. Now that's all assigned. I can do a virtual mold here. I get a consistent look and feel with our flow simulation computational domain. I can resize that on the fly with a drag and drop, really easy. And then the last thing, if I'm going to do a full cooling analysis, I would go into the cooling channel definition. I've got sketches down here for that. Just give some reasonable sizes here, and off we go with that. I'll assign that sketch. That's good. Let's go ahead and pick the second one here below, assign it, and off there it is. So we've got our cooling channel, and it's talking about updating the virtual mold. That's fine. It's prompting me for something that I need to pay attention to, so I'm going to read those messages that come up on the screen. I tell everybody in my training classes, when you see an error message or some kind of warning message, don't just dismiss it. It's easy to do, and especially if you're a little bit frustrated at that point. So don't dismiss them right away, just read them and act on it. It's usually going to give you some good information. Basically, then we just go down the tree here and set up boundary conditions, for fill settings and stuff like that. To save a little time, I'm going to jump over into, actually, no, I'm going to show you the mesh. Let me show you that real quick. The mesh process is greatly improved as well. We used to have a 6-step process to get a solid mesh out of the model. I'm going to use defaults, and I'm just going to create my surface mesh so you can see that. And if I'm happy with that, I would proceed to the second and final step and create the solid. And if there were plastics users in here that have used previous releases, they'd be clapping right now, because this is really big. We used to have to go through 6 steps to get to this point. So you can see a cross section of the mesh there. We've got a very good hybrid mesh to take care of all of the geometry, and it's all captured really well. So let me go, like I said, into a solved project here, and I'll just show you the results. Nothing's really changed there. It's same great interface for that, and we've got the consistency now on the upfront where we're setting things up, and this thing's going to load up. I'll switch over to the plastics tab and off and running. What do you guys think? Does this look like something? I think somebody said hope to be a plastics user. How's that look? Thumbs up? Okay, very good. So with we've got things in here like setting the injection location. That's geometry based now. You can see it's based on the face of the runner there. The coolant input as well. So I've got a lot of things that are related to setting up using the geometry as opposed to the mesh in previous releases. Just show you real quick the results here. Loading up the flow calculation that was done. And once we get that loaded, we can animate that. We can show some isometric clipping options here, or iso surface rather. Let me just go ahead and animate that. That shows really well. You can see it flowing around that insert and giving us the fill time plot. We have lots of information we can get out of this. Notice that a packing solution was done as well as a cooling. All right, so that's plastics. I will move on so that we don't miss something later, but that is our plastic simulation tool. When we'll have some opportunity for some questions afterwards. So anything comes up, keep that in mind, and we'll chat about that as soon as I'm done here. So let's go into the flow simulation. We saw hands raised for flow, some flow users out there. Really great program. If you've not used it and you have access to it and you need to do some flow calculations, by all means, go ahead and take a look. You'll be very pleased. So I'm going to show you some stuff that came out. The Sunlight Properties import came out in 2016. So we're going back from that first year of what we're covering here. Multi-parametric optimization came into play. We have a heat flux plot that we can show as well. Lots of really great stuff here. So I'm going to show you this model. It's basically a solar cooker. My kids and I went out to the driveway. We got some plans off the internet. We drew this up in sheet metal and cut it out of cardboard and put it together on the driveway, put some aluminum foil in there to act as a reflector, and it worked really well. And in fact, it worked so well that we had some plastic in there to separate the regions, and we literally melted some of the plastic. So needless to say, we didn't eat any of the stuff that we cooked out there, but it did a really fine job. I'm also going to show you the free surface tool, which came out in 2018. All right, so let's jump into SOLIDWORKS and take a look at that. Has anyone done any animations in SOLIDWORKS? Just basic animations? Okay. If you weren't aware, we can animate the shadows that we get. You know, we can turn on real view graphics, we can turn on shadows, and this has sunlight that's been turned on. You see here in the tree, I've got sunlight turned on, and if I animate this, you'll see that shadow move across the ground there when it moves. So the sunlight was set for Chicago, Illinois, from 10 a.m. to 12 p.m. on Memorial Day weekend. So you can see that angle of the sun there, the shadow moving across the ground there. Well, with simulation, with flow simulation, we can import that into our flow project and use that as a radiation source. That came into play with 2016. Let me show you that. I'm going to turn off my plastics, turn on flow. So this is really a great tool to work with solar radiation. Oh, I turned on the wrong one. You guys saw me do that, didn't you? You didn't catch it, you didn't tell me, so no worries. Here we go, flow simulation. So I've got several projects here. If you're not familiar with flow projects are grouped or can be linked to configurations. So you can have several projects under each configuration. You can do what-if scenarios where you change the geometry. You can clone a project and apply it to that other configuration, that geometry change. And I'll show you in a second how you can leverage that even further and do a parametric study. If you haven't used parametric study, that's huge. So we've got this transient, that 2-hour window of that sunlight going from 10 a.m. to 12 p.m. Anybody from Chicago out there? Some Chicago, one Chicago, that's it? What are the favorite foods in Chicago? What are the famous foods in Chicago? Pizza and Italian beef. So like the hot dog kind of a shape? Yep. So what we're going to do is we're going to cook some Italian beef here with flow simulation. If you look at the cross-sectional view here, I've got a simulated rack of Italian beef for you, just for you, Sean. And we're going to cook that with our solar cooker. And first thing we'll do is we'll look at the transient simulation of that to see how that temperature in that cook chamber changes. I've got the project set up here, and you'll notice that I've got several goals for that to track things. I'll talk a little bit more about that in a minute. One of the new things with flow simulation that's really great is this thing called the Transient Explorer. So I'm going to load the results for this 2-hour transient simulation. I'm going to show the surface plot so you can see how the ground and the cooker heats up over time. And I've got the little controls down here to show how, or to control that animation for you. So there's my solar cooker. You saw that shadow move when we were looking at it from the top here. This is the temperature profile, the color-coded temperature profile of everything, and you can see the effect of that shadow moving across the ground. We've got a cooler area back there that we can tell that sun is heating things up. And there's our temperature. Now, you know, I told you if you see something that you hadn't seen before, feel free to blurt out, I didn't know that. I didn't know we could do that. Well, I almost did that in a presentation yesterday. I was with Joe Galliera. He's affectionately known as Flow Joe. He works for SOLIDWORKS. And he showed me in this tool, you can right-click on it, and you can go to options. And I had no idea we had that in there. We can change the settings for frames per second. And, you know, a couple of things in here, it's like, wow, Joe, I didn't know we could do that. So I almost blurted it out, but he would have probably been thrown off by that. So I haven't heard anybody blurt it out yet, but hopefully you're thinking about it. Okay, so that's our Transient Explorer for that heat. And what I can do also is look at a section plot. So let me just drag this over to the noon hour over here. I'm going to drag it over to the right. I'm going to hide that surface and then show a cut plot. Cut plot is like taking a slice through it and show me the temperature of everything. And as you can probably tell, I'm using a external analysis here. The computational domain is our volume that we're solving for. And you can see the extents of that with the cut plot here. So I've got a cut right through the middle of that. And if I make the geometry transparent, you can see through it, and you can see about a 50% transparency ought to do it. And you can see the air in there, the temperature profile. So red is hot, of course. Blue is cold. We got about a 63 cold level and a 200-degree hot side. I'm going to animate this, and even the flow streamlines and everything are going to animate for me over time. And you can tell that the angle of the sun is coming in from here, left to right from the top, and you can see the backside of this box being heated up significantly. And recirculation in there. I've got two separate chambers. The cook chamber is isolated from the top chamber. You can also see the plume of the warmer air coming up through natural convection. I've got gravity turned on. You can see that coming up and flowing upward as it's heated up.
Can you like analyze UV levels? You can change the frequency of the light that's being radiated from the sun?
We can work with the spectrum, yes. It's going to require, I believe, and I'll verify it afterwards, but we can, I think it requires our HVAC module, add-on module, to be able to do that, but I'm pretty sure, and I'll verify that for you. The question was, can we change the frequency of the spectrum of the solar input? And yeah, I believe that's going to be the case for our HVAC add-on module. There's two modules that you can add onto the basic program. The basic program is very complete. HVAC gives you things related to heating, ventilation, and cooling. And electronics cooling gives you extra functionality related to cooling electronics, as you might imagine. All right, so let's see. Let me show you just how some of this stuff comes into play. We've got the Transient Explorer has to be turned on in case you want to do this. Go into your calculation control options. The Transient Explorer needs to be turned on here in the lower part of that window. Basically, you want to save specific data more frequently with this Transient Explorer, so you get these good animations. The rest of the saving is done up here for the full solution on a periodic basis. So that's the Transient Explorer. Another thing that came into play within these last few releases that I'm mentioning, nested iterations. So a transient study, as you can imagine, is going to take a long time, especially if you have a small time step. The nested iterations allows you to set up a slightly larger time step, and you'll see that here. You can have a larger time step. Nested iterations does some internal manipulations of that and allows you to progress through the solution with that very coarse time step. So it's a super powerful functionality that has come in recently as well. All right, so what I'm going to do is I'm going to unload these results, and I'm going to switch over to show you a steady state analysis at 12 p.m., this one right here. So this is at high noon in Chicago. We're going to cook our Italian beef and in our solar cooker. And I'm going to introduce to you this design of experiments method to do some parametric studying. This is basically the same study that I had before. I've locked the sunlight input at 12 noon, and I'm solving steady state, right? Well, what I've done is I've gone into a parametric study that allows me to change a couple of variables and come up with the optimum of those variables to get the hottest temperature in there. I didn't show you, but I've got a goal in here for the average temperature of the solid. That's the solid of the food that I'm cooking. That's that little rectangular shape in there. So I've got that goal set up. I've got a couple of dimensions here. I've got one that's related to the angle between the base of the cooker and the surface of the ground. And that is done basically through the mates within the assembly here. When you set it up, you go tell it, oh, I'm going to use this angle mate here. I'm going to grab that and let it change that within a range that I have for it. The other one I have here, this lower dimension, is the height, or the height of the cook chamber. I'm going to let that vary between 8 and 12 inches. Maybe there's some sweet spot in there with the height of that would allow me to get the optimal temperature. And maybe combined with that, there's the angle of that base to the horizontal that would allow me to get the best heat up. So with the next tab here you'll see is the output parameters. That's our goal of that maximum temperature that I'm monitoring. And then the scenario. I've got this method uses, like I said, design of experiments. So I give it those two variables in the range that it can change. I tell it to go ahead and create 10 scenarios, and that's what you see here. I've got the 2 dimensions that it can change. It came up with these 10. I ran those, all 10 of those, and at this point I'm ready for it to tell me what the optimum angle and height of that box is. Now you might think 10 of these I'm going to solve for. That's a lot of stuff to solve. That's a lot of time, right? Well, don't forget that flow simulation has the ability to specify multiple solutions at the same time. I can do 2 solutions at the same time. I just tell it how many cores of my processor I can use. And so I'm doing 2 at a time. So it's like solving the time it takes to solve 5. So at this point, with that information that it's gained, I'm going to tell it to find the optimum for that. And you see I have an objective function that I can set up over here. And I'm telling it to just give me the maximize the, let me bring it over here so you can see everything. Maximize the volumetric temperature of that food that I'm cooking. And I've got a weighting factor. I can have multiple objective functions in here. And I'm just going to tell it, add that point, that design point. And it's telling me here, as you might expect, 10 degrees, and the 10 degrees, which is my top end of my range of the angle, and an 8-inch height of box. Kind of makes sense. Tip it more towards the sun, make that box smaller. So it came up with that, and it's telling me here that the maximum temperature you're going to get out of that is about 251 degrees for that food. Question?
Can you set
Yes, as part of SOLIDWORKS, we can reference that information, right? Okay, so if you look at the highest that it actually calculated, it's right around 249 here, and so using design of experiments, statistical analysis, it came up with this combination is going to give me the best. So I can go and have it create a new project based on that geometry. And it's just warning me, you're going to change the geometry. I'm saying, okay, that's all right. So there's my tilted 10-degree cant on that orientation, and it's got the smaller cook chamber in there. So really powerful tool here. I would encourage you to dig into that. There's a couple of other ways we can use design studies. We can use what-if scenario. What-if analysis, I can give it several variables and have it just give me solutions for all those combinations. I can do a goal optimization, which takes a single variable and optimizes, kind of like what we did here, but for a single variable. So very powerful tool. I encourage you to check that out. Was anybody aware of that? Anybody aware of that one?
No, I got a question. I wasn't aware of it.
What's that?
I said I had a question. I wasn't aware of it.
Oh, okay.
Is there a way to display it in a graphical form, so for more like a graphical analysis of all the outputs, or a way to export to a Excel, spreadsheet to make a graph? Or? Yeah,
we can do several things with that. We can show the I think it's called the optimal surface plot, where you see all the variables at once. Yeah, we can do that type of information. Yeah. The question was, can we look at a graphical representation of this? So yes, we can. All right, so let me jump into that free surface and show you that. The free surface came into play in 2018, and it was probably one of the most requested enhancements that we've had in a long time. What I have here is a spillway, a simulation of a spillway. And you'll notice I have these blue colored parts in there. These are separate parts, and they represent a static pool of water, okay? So I have a boundary condition at the bottom here to an inlet volume flow, where I'm going to push water up from here and let it spill over and then flow into that standing pool there. And so my engineering background, I started in civil engineering, so I've always been fascinated with civil engineering, water resources type things, and things like flow over weirs and spillways and stuff like that has always fascinated me. So when I saw the free surface come into play, I thought, I bet it can simulate that and show me where that hydraulic jump develops within the spillway. And that is exactly what we have here. So I'm going to load this up. I want to point out another thing that we can do. What I've loaded here is the final time. The free surface is a transient type, and I should maybe back up a little bit here and go into the settings for that. When you turn on free surface here, you'll notice that it is a time-dependent type of analysis. It has to develop over time. We've also got gravity turned on here. So these will take a little while, and you will have to have some good refinements of the mesh wherever you're going to have that free surface interface. It's using the volume of fluids method to come up where that free surface is. But it's super powerful. So let me show you the ISO surface. And here we are with the final time step here, 10 seconds of flow. And you see we've got the hydraulic jump there with that standing wave. You can see where it's spilled over the other side down here. And I have a cut plot in here that shows the volume fraction of water. That's probably the best parameter to show to show that layer, that interface, I should say. And you can see that thin layer as it goes down the spillway, and then we're using that, or the natural phenomena is to use the turbulence to dissipate the energy of that fast-moving flow, encountering a more stagnant flow. So a very powerful tool there. And let me show you a couple of time sequence type plots here that really illustrate that well. Oh, and I forgot to, after the oven, I forgot to show you, we have the heat flux plot. This is the heat flux plot from the solar oven that I showed you before the free surface. You can see the transport of heat from convection in blue, conduction in red, and radiation in yellow. That's a very nice way to map things out and see where you are. So back to the free surface. Here's a couple of screenshots of the time lapse. 1 second into it, 3 seconds into it, you can see the interaction there between the flowing fluid and the standing pool. And now we're starting to get the hydraulic jump set up at the 5-second mark. And here we are at 7 seconds, and we're starting to spill over the backside there. I think that was on the previous one. Let me go back. Yeah, we've spilled over the backside. Back to 7 seconds, and you'll notice when I go to 9 seconds, doesn't change much. That standing wave has been established. So really cool, I think, to do things with where you have a free surface involved. So this could apply to tank filling and emptying, any type of an interface like that, and as well as, I haven't done it yet, but some people have used this to study boats as they move along in the water with the wave that gets developed, the wake and everything. So super powerful tool there. Let's jump into simulation, finite element analysis. I think we're doing pretty good on time here. Simulation evaluator is new for 2020. It's a nice new utility to help organize your study and make sure you've got things set up even before you kick it off. And then we'll jump in and I'll show you some things related to the stress hotspot detector that came out in 2017 and a singularity check on 2018. I'll also show you I'll give you a brief look at the topology study that came into play with 2018. So a lot of applications for this with the 3D printing, especially now that we have the metal 3D printing. I've got this bicycle crank arm that I could print in metal and actually literally use. And this is leveraging the Dassault Simulia technology for topology. And then I want to go back one release. I'm going to show you some new old stuff. So 2015, we had a really nice new feature. I'll save that as a surprise. Simulation evaluator, new for 2020. We basically get 3 different things that we check. You can run this before you start your study and before you run into any issues. It checks for where the results files are, where they're going, do you have enough space there, stuff like that. Have your materials been applied to everything? Is your mesh volume good and comparable to the actual part volume? When I started this crank study, I solved it in another location, moved it, opened it up, and the program couldn't find the CWR results file. Little bonus question, who knows what CWR stands for? And Bill, you cannot answer, sorry. CWR. What did I hear someone?
Cosmos Works results.
Cosmos Works results, very good, yes. We have some of the vintage naming still in the program. Cosmos was the program that was developed back in 1982, I believe, as a standalone, 1981? Okay, thank you, Bill. 1981, Structural Research and Analysis Corp developed a very powerful standalone tool called Cosmos. SOLIDWORKS bought it, and I can't remember the year, 2002 or so, and called it Cosmos Works to go with SOLIDWORKS for all things finite element analysis. So there's some long history with this program. So, you know, program can't find it, it needs it if you're going to be able to reference your results. I moved it to this folder here, this subfolder. I like to keep things kind of tidy. And so, well, I'm just going to, in this evaluator, I can pick the link to go edit the properties and change that. I've done that, I've moved it, it comes back, it says, yep, I found it, let's go ahead and validate it. Click there to validate. Next thing you know, it gives us the green check mark. Thumbs up, we're good to go with results. So that's the simulation evaluator, nice little utility. Let's jump into the program now and talk about all things finite element analysis. I'll go into my crank here. I'm a cyclist. Any other cyclists in the audience? Okay, great. Thank you. I do road and mountain bike cycling, and you'll notice this is a clip-in type pedal. And who's ridden with a clip-in pedal before? Okay, those of you that did you crash it the first couple of times riding? Yes? No? Okay, good. Yeah, you're pretty good. Most people crash the first time you ride it because you not realize you're strapped in, and you come to a stop sign and you stop, of course. And then what happens when you stop on a bicycle? You got to put your foot down. And I've embarrassed myself a couple of times learning to use these clip-in pedals. Let's just leave it at that. This is a assembly. We're in an assembly file. We're going to look at a simulation of this. And I know that that bicycle pedal is an off-the-shelf item. It's been fully analyzed. It's strong enough to hold whatever. I don't need to use it in my analysis. So what I'm going to do is I'm going to leverage the configurations, and I'm going to switch to a configuration that doesn't have it. And I'm going to replace that with a remote load. You see this icon out here. This is a remote load that represents my full downstroke at 175 pounds on that, when that crank is at this horizontal position. It's positioned out there at the center of the application of that from the cyclist. I've got the chain rings restrained up here to keep things locked in, simulating that we're pulling on that chain. And I've got some other restraints in here to stabilize the model. So this is my static study of an assembly. And I showed you the simulation evaluator. You access it from within the right-click menu here. You can get to that really quickly and run that. And then you've got the ability to also do things in here like collapse the tree as you know, one of the new things, it would get kind of cluttered as you're working through your studies, and when you collapse a folder and then you pick on a part, the folder expands again. So if you do that enough, you're working with the model, you want to collapse that quickly. For 2020, you can just hit Shift-C and everything's nice, collapsed, tidy for you. So that's pretty neat. Our remote load that I've applied there, if I edit that, you'll notice one of the other new things. Has anyone used remote load before? Show of hands? Okay, so a few of you. The new thing about that for this release is that now, like other things like pins and bolts, we can do a distributed connection type as opposed to the connection being fully rigidified from the result from putting this on that face. Now I can use this distributed connection to make it even more realistic for us. So. Hey, thank you very much. I didn't know we could do that. I heard it. That's awesome. Thank you. Did I already give you a prize?
Someone said behind me at the same time.
Oh, okay. Who said it from behind him?
So you gotta split it.
Catch me afterwards. I got another tumbler for you. Appreciate that. All right. So let's see. Other things that we can do in here. You know, we can assign materials at the SOLIDWORKS level, right? And that stuff that material has density in it, so we can know how much things weigh. I can also now in simulation look at mass properties that we're going to be reflecting whatever changes I've made to the material definition within the simulation side. So this is going to be our accurate representation of the mass properties for this, regardless of what was done before in the SOLIDWORKS side. As you can see here, I've got different materials applied, some carbon steel, some aluminum in here. And this brings me to another point here. You see these icons. If you don't recognize those icons, those are new icons. We can now mix draft and high quality mesh in a static study. So that's pretty big, because you get a large assembly, you get a lot of mesh refinement, you're going to get a lot of degrees of freedom on a high quality mesh, which their high quality has 10 nodes on a tetrahedral element. Draft quality has 4, so you've got to reduce that degree of freedom count. And so what I can do is I can say, well, apply draft quality to that chain ring if I don't want it to be that high quality. Save some overhead, right? So I can mix those up in a model, and that's what those icons are all about. In here we've got, I showed you the remote load and fixtures. Let's jump into results. You're probably tired of seeing that as is. Here's our results. With that remote load applied, I've got the ability to control things really easily with the color bar here now. We used to have to right-click on the plot on the left side. Now if I want to change the maximum value, I just click on it and type in whatever I want to show there. So that one is right at 20,991, so maybe make that 18,000. And accept that, and my range changes based on that new level there. Ready to reset it, just go ahead and give it a reset here. I can toggle on and off the maximum annotation right there. Lots of control there. I can also use some right clicks in here and show the mesh, for example, animate, change what's shown here, fringe options. So lots of great control right there in the graphics area. Another relatively new thing that's come across is called mesh sectioning. If I look at this plot that I've created, and I can take a cut, it's kind of like we've had the section plot or the section clipping for our stress results before. Mesh sectioning allows us to get a little bit more detail about what that mesh looks like within the model itself. Switch my view there, sorry about that. So mesh sectioning is super powerful. Lets us get a little bit more interrogation of what's going on inside the model. All right, let's move on to the hotspot detection. So I've got a nice model that shows that here. So stress hotspot is looking for irregular patterns or irregular change in the pattern of our stress field within the model. In this model, I've got the same remote load out there, and I've got a, let me see that one, let's hide that one. I've changed my restraint here, so I'm reacting that torque on a couple of those spline teeth in there. You see that in there, the green arrows. That's resisting all of that torque as opposed to going through those chain rings like I had before. So if you look at the plot there, looks pretty good. If I didn't have this marker turned on, you'd say, hey, it looks fine. If I turn off that marker, you know, you're like, okay, well, where's the red? I don't see that. I'm expecting it to be here. Well, if you look closely in this area, it's got a fairly poorly shaped element there, and it's got an area where it's suspect as far as being a real stress. I can do this Hotspot Diagnostics tool, give it a sensitivity factor and run that, and you say, yep, you've got a hotspot in here. Let's see what that's all about. Once that has run, you'll see the hotspot is going to be turned to a gray color. Well, it's in there, but I can isolate it here nice and easily and say, yep, there's my problem area. Well, is that a real problem, or is that a stress concentration that I need to figure out if it's real stress? What is that real stress? Or is it a singularity? Singularity is, in stress analysis, it's a point where you have a sharp corner to come together, and it's a discontinuity. The math cannot, it's an infinite point of stress because of that sharp corner. It's true for any finite element analysis. So if I run the stress singularity diagnosis, I'll just use the defaults for that. What it does, it refines the mesh according to my directions. I'm using defaults. It refines it a couple of steps along the way, and it checks to see if this is something that's just a stress concentration or if it's a singular point in the math. And it's telling me, yeah, you've got a singularity there. So there's the refinement that it's done, and it's shown me that it's a singularity, and there's how it's ramping up in the stress as increased that mesh refinement. What do you guys think? This looks like some good stuff. Anybody else seen some good stuff that you might be able to use? I see a head shaking there. Yeah, a couple of nods. Good, good, excellent. Hopefully I'm keeping you guys awake too. That's it's tough being right after lunch, right? All right, so one of the other things that I want to show you in this model is the topology study. Topology comes into play with Simulation Professional or better, and I've got a model here that uses that. The new thing for the latest release is that we can use load cases. And load cases have been around since, I believe, 2015. Has anybody used load cases to run multiple loads on your model? Okay, we've got a couple that have done that. Topology can now be used within the topology study. You can run multiple load cases, and what it does is it's going to consider both of those cases. It's not going to combine them and give you just the shape for that combined load. It's going to consider both of them and come up with your optimal design. So here's my load cases. It's basically a load simulating, this one simulating a full downward position of the crank, and then the one that I ran before with when the crank's in the horizontal position. So I push on that downstroke, and I get to the bottom, and I've still got a pretty significant load there at the bottom of that stroke. So we need to know what's going on there and figure out if the you know, what's the optimal shape for that. So the load case manager takes all that into account. Basically, real quickly, and I'll give a plug for Mr. Bill Roos in the back. He's going to give a full session tomorrow on topology analysis. So I'll just show you briefly. We set up the topology to minimize the displacement, look for the best stiffness to mass ratio. In my case, what I've done is I've told the program to minimize the displacement of this point, this vertex right here. I don't want to see that twisting or bending on me too much. I want to keep that as stiff as possible so I get that force going into the crank, that downstroke on the crank. Check out Bill's presentation tomorrow to get the full-blown show there, and I'm going to show you what it came up with for that combined load. This is a kind of a funny looking plot if you've never used it. It's basically I've got to keep this much mesh, or I can get rid of some of this much mesh. That's basically what you're looking at here. The yellow is stuff you got to have if you want this to be able to handle these loads. And I can remove some of the material over here if I want to minimize it. I've got another simpler model. Let me jump over to that. Let me show you some screenshots from a simple model that it shows it very clearly. If you look at this one, you'll see the outline of a basic block here. I just drew a random block, and I put a couple of holes in it, and I fixed this bottom hole here. As you see all along the way, these are all fixed to the bottom. And in this one, on the left, I've got a horizontal load, and then on the middle, I've got a vertical load, and in the right, I've got both of those loads combined and the optimization results for that. So you can see if I overlay the horizontal and the vertical, I'm not going to get this optimized load. It's taking them into consideration. It's not just mapping them one over the other. So it's doing some pretty powerful calculation to come up with that for you in the background. All right, so last thing I want to show you in simulation is, there's Bill's plug. Catch him tomorrow, 1:30 p.m., topology. Bonus stuff, new old stuff. If I showed you this tree on the left here, if I show you this tree on the left, would you believe that I created that animation that you see on the right? All in favor, raise your hand. 1, 2. Oh, we got a couple. Well, I did. I created this stress animation from this part here. This empty part has no solid or surface geometry in it. And basically, what I'm talking about is 2D simplification. 2D simplification is super powerful. I didn't want to pass it by. 2015, it came into play. Here's my empty part, but it's got some sketches in it, and here's my nonlinear representation of that. There's my stress for energizing this metal sealing device. Okay, thank you. All right, so let me wrap it up there. We basically, we have seen a lot of good stuff, and are there any questions about what you've seen today? Anybody else have any other questions? Yes. Oh, Mr. Anlicker, Kurt Anlicker from SOLIDWORKS, you have a question for me.
Take over your presentation for about 2 minutes?
Yes, you can. Let me...
Awesome. In case you missed it, we've been talking about this since Monday morning in general session, and our goal is to pop in on sessions like this and show you some new functionality that's coming soon. Soon probably means the next release. It's a technology preview. So we've done a few of these already. So yesterday, we did sheet metal and assemblies. Earlier today, we did one on the user interface. All of these you can go watch. They're on SolidWorks Live, live.solidworks.com. Check them out there. It's a great content, great information. So let's take a look at some simulation stuff that's coming. So I think everybody in the room agrees we want high accuracy results as fast as we can get them, right? So Kurt already talked about this. This release, we added draft and high quality mesh in the same study. We also did another thing, which is changing the default bonded contact from compatible to incompatible mesh. Okay? We did this because we worked collaboratively. Actually, it's all one simulation team, right, Lavi? It's all one simulation development team. We did that because we worked with Simulia so we can get better results from incompatible mesh. Coming soon, that image showed you can get better results on incompatible mesh where you have mesh variations, not just geometry variations like you're seeing in 2020. Now, in addition to that, we're improving a big project to improve blended curvature-based mesh. Okay? In fact, you'll see results like this in the next release compared to what we had in the current release. So this is almost a 50% improvement in the performance in mesh. That also relates to a pretty significant performance increase in getting your results. Hopefully you're paying attention to the chart on the upper right as well, because what good are faster results, Kurt, if they're not accurate?
Absolutely.
They're not worth anything. So of course they have to be accurate. As you would expect, they're doing a lot of work to ensure you get very accurate results, very good quality with incompatible bonding on your mesh studies using this new technology with blended curvature-based mesh. So stay tuned for that. Stay tuned for the beta program this summer. If you missed anything on this session, the whole session has been recorded, so you can check all of that out on live.solidworks.com. That's all I have. Have a great show, and please finish watching Kurt's presentation.
Thank you, Kurt. Appreciate that information.